Welcome to the only podcast that can make entropy sound sexy. Let's get thermodynamically dangerous. This is mechanical engineering made simple.
I think that it's officially my favorite introduction we've ever done.
Hey, we try, right? But honestly, today we are getting into some seriously foundational stuff. We're doing a deep dive into the thermodynamics of combustion.
Right, which sounds incredibly dry, I know, but it is actually mind-blowing once you really get into it.
Completely, because, you're looking at cars and boilers every single day, right?
Hmm.
But today we are going to look under the metaphorical hood to understand the invisible laws governing the power they actually produce.
And why perfect efficiency is so, elusive in the real world.
Exactly. Our mission for this deep dive is to demystify how burning actually works on a molecular level. We want to translate all that dense engineering math into real aha moments.
Yeah, to show you how a gas turbine actually powers the world around you.
But to do that, we kind of have to start by completely redefining what a flame actually is. Because before we can understand how an engine extracts power, we have to completely rethink what it means to, burn something.
Yeah, the source text we're looking at today makes this really clear. Most people look at a fire and think, oh, it's adding heat to a system.
Right, like the fire is creating the heat out of nowhere.
Exactly. But it's not. Combustion is not adding heat. It is an exothermic oxidation process.
Okay, let's break that down for everyone, because exothermic oxidation process is a mouthful.
It is, yeah. Basically, it just means that the process releases chemical bond energy that was already contained in the fuel. It just releases it as thermal energy.
So the heat was locked up inside the fuel the whole time.
Exactly. It was already there. Think about hydrocarbon fuels, like natural gas, methane, octane, or even alcohols. They combine with air to produce carbon dioxide and water.
And the source describes this as, I really love this phrase, a molecular barn dance.
Yeah, that is a great analogy. It's a true statistical process where these molecules are constantly breaking down. We call that dissociation.
Right.
And then they immediately recombine. And the tempo of this whole barn dance is controlled entirely by temperature.
So higher temperatures mean a faster dance.
Exactly. They break apart and recombine with a lot more ferocity.
So, okay, think about it like a giant Lego set, right?
I am always here for a Lego analogy.
Well, imagine you have a spaceship built out of Legos. That's your fuel and your air molecules. To burn it, you essentially smash that spaceship to pieces. You break all the bond.
Right, the dissociation phase.
Right. And then you take those exact same scattered bricks and you build a castle instead.
Yeah.
The castle is the carbon dioxide in the water.
Yeah, that is basically exactly what happens.
And then the key here is that the number of total Lego bricks, like the actual mass of the atoms, it stays exactly the same. But the number of finished structures can completely change?
Yes, the total mass is always conserved. That is absolute. But the number of molecules doesn't have to be.
Wait, really? The molecule count can just drop?
Yeah, totally. Like you could have 3 molecules of reactants enter this process, and they can combine to produce only 2 molecules of products.
Oh, wow. So you have 3 full structures, you smash them, and you only build 2 new structures out of all those same bricks.
Exactly. The mass of the bricks is identical, but you just have fewer overall structures.
So since this is basically molecular construction, how do engineers know, exactly how many bricks to put into the mixture in the first place? Like, how do they get the perfect reaction?
Well, they use stoichiometry.
Stoichiometry.
Yeah, stoichiometry is this clearly defined fixed ratio of the masses of air and fuel that results in complete combustion.
The perfect recipe.
Right, the absolute mathematically perfect recipe. For instance, for 1 kilogram of methane, you need exactly 17.17 kilograms of air.
17.17. That is super specific.
Very specific. And if you don't hit that ratio, things change drastically. Let's say you have a weak mixture, which means you put in excess air.
So more than the 17.17 kilograms.
Right. If you have more air than required, that excess air just passes straight through the system.
It doesn't even react.
No, it doesn't chemically react, but it still heavily impacts the reaction because it absorbs energy.
Oh, like a thermal sponge.
Yes, precisely.
Yeah.
It soaks up that energy, which significantly lowers the overall temperature of the combustion.
Okay, so that's a weak mixture. What about a rich mixture?
A rich mixture is when you have insufficient air. So you have your fuel, but you don't have enough oxygen to go around.
So the atoms have to fight over it.
Basically, yeah.
Yeah.
The hydrogen is incredibly reactive, so it takes the oxygen first to make water. And that leaves the carbon partially oxidized.
Which means it doesn't turn into CO2.
Right. It doesn't have enough oxygen for carbon dioxide, so it produces carbon monoxide or CO.
which is highly toxic.
Highly toxic, yeah.
Yeah.
And rich mixtures are also just incredibly wasteful.
Wasteful how? Just from unburned fuel.
Not just that. The text notes that burning methane in a rich mixture, say, at an equivalence ratio of 1.2, it only releases 76.5% of the fuel's potential energy.
Wow. You lose nearly a quarter of your energy.
Yeah, because that unoxidized carbon, the stuff stuck in the carbon monoxide, it never releases its full thermal energy. It just goes right out the exhaust.
Okay, I have to push back on this, though.
Go for it.
If a stoichiometric mixture is the mathematically perfect recipe, and it gives you complete combustion and max energy, why would any engineer ever intentionally run a weak or a rich mixture? Like, why not just build every engine to run stoichiometric all the time?
That is the big question,
Yeah.
right? But you have to remember, we are dealing with the physical real world. If you run a perfect stoichiometric mixture inside, say, a gas turbine, the temperature gets so high it will physically melt the metal blades.
Oh, wow. So it's just too hot for the machine to survive.
Exactly. So they intentionally run a weak mixture. They pump in tons of excess air to act as that thermal sponge you talked about, just to control the temperature so the engine doesn't melt into a puddle.
Okay, that makes sense.
And historically, with rich mixtures, sometimes you need a massive surge of power quickly, or you're trying to start a freezing cold engine. But generally, yeah, you want to avoid rich mixtures because of that massive drop in efficiency and the toxic CO gas.
Right. So, okay, let's say you figure out your perfect recipe. You know if you need it weak or stoichiometric.
Right.
The engineers still need a way to mathematically calculate exactly how much energy that specific recipe is going to drop into their engine, right?
They do. And this is where we open up what the text calls the energy checkbook. You have to figure out heats of reaction, but it changes depending on the system you're using.
Changes how?
Well, you have constant volume systems and constant pressure systems.
Okay, so like a closed box versus an open pipe.
Essentially, yeah.
Uh,
A constant volume system is like a closed combustion bomb calorimeter.
a bomb calorimeter sounds dangerous.
It's just a very thick steel box, honestly. But because the volume can't change, it measures the internal energy of the reaction. Every ounce of energy goes into raising the temperature and pressure inside that fixed space.
because it can't push out.
Exactly. But a constant pressure system, like an open gas turbine, is different. As the gas expands, it has to push the surrounding atmosphere out of the way.
Right, which takes physical effort, work.
Yes. So a lot of the energy is used just doing that pushing, rather than heating the gas.
Yeah.
So for constant pressure, we measure the enthalpy of reaction, which accounts for both the internal energy and the mechanical work done pushing the air.
Ah, okay. That's why enthalpy is such a big deal in engine design.
Exactly. And when you hear people talk about the calorific value or the heating value of a fuel,
Right, you see that on spec sheets all the time.
that is actually just the negative value of its heat of reaction. It's the exact same concept.
Okay, but calculating this enthalpy for these massive, crazy, complex molecular chains shearing apart in a millisecond, that seems impossible to do perfectly.
It would be if we had to measure every single intermediate collision. But thankfully, we don't have to. We use Hess's law.
Hess's law. Okay, refresh my memory on that one.
Hess's law states that the heat liberated by a reaction is completely independent of the path it takes between the initial state and the final state.
Independent of the path. Okay, so it's kind of like climbing a mountain.
How do you mean?
Well, if you're trying to figure out your change in elevation from base camp to the summit, it doesn't actually matter if you took this crazy, winding, complicated zigzag path up the rocks, right?
Right.
Or if you just flew straight up in a helicopter and dropped on the top. The total change in your energy, your elevation, is identical either way. The middle stuff doesn't matter.
That is a brilliant analogy, yes. Because energy is a state property, just like elevation. So engineers can calculate complex molecular reactions simply by adding up the energy of smaller, simpler, well-documented reactions.
So they don't need a supercomputer to simulate every single atom?
No, they just use addition and subtraction on standard chemical tables. It is incredibly elegant.
It is, but I feel like this is where the theory hits a brick wall.
The real world.
Yeah, the real world versus the whiteboard. Because Hess's law and stoichiometric equations, they look so beautiful on a classroom whiteboard.
They really do.
But what happens when you actually put these perfect equations inside a freezing cold solid metal engine block that has moving parts?
Everything gets infinitely more complicated. Because on the whiteboard, we're usually assuming adiabatic combustion.
Right. Adiabatic meaning perfect insulation, right?
Exactly. It's the theoretical ideal where absolutely zero heat or work is transferred to or from the system.
So all the energy stays right there in the gas.
Right. In this perfect scenario, enthalpy stays completely constant. 100% of the chemical energy goes directly into heating the combustion products.
But engines are essentially the exact opposite of that.
Precisely. They are non-adiabatic by design. You have these incredibly hot, expanding gases, and the first thing they do is slam into the cold metal walls of the cylinder.
Which sucks the heat right out of them.
Right. And then, as the piston moves away from top dead center, which is producing the mechanical work we want, it is actively reducing the internal energy of the products.
So the very act of using the power fundamentally cools the reaction down.
Yeah. It's kind of a tragic paradox, isn't it?
It really is. It's a fascinating irony. The work the engine is designed to do, moving a piston to power your car down the highway, literally saps the internal energy from the combustion process itself.
You can't cheat the first law of thermodynamics. If you extract work, you lose internal energy.
So thermodynamics can give us a reasonable assessment of all of this on paper.
It gives you the absolute maximum boundary of what is possible, yeah. But it can't completely model everything, especially things like pollutants.
Right, because if things are cooling down rapidly by hitting a cold piston wall, the chemical reactions must just kind of, start.
Basically, yes. It's called quenching. The flame gets too close to the cold metal, temperature drops, and the reaction freezes in place before the fuel can fully oxidize.
Leaving unburned hydrocarbons.
Exactly. And thermodynamics on its own can't really model that. Pollutants are largely caused by fluid mechanics, like the poor mixing of the fuel and air in those fractions of a millisecond and the actual rate of the chemical reaction.
Which requires a whole different set of equations beyond basic thermodynamics.
Yeah, you need complex fluid dynamic models to actually track the physical reality of the gases swirling around inside that cylinder.
It's wild to think about how much chaos is happening under the hood while you're just sitting in traffic drinking a coffee.
It's a miracle it works as well as it does, honestly.
Seriously. Well, this has been an amazing deep dive. I mean, to quickly summarize for everyone listening, combustion is not just adding heat. It's this temperature-controlled molecular dance that unlocks pre-existing bond energy.
Right, the energy was there the whole time.
And getting that stoichiometric recipe right is absolutely crucial to avoid creating toxic CO and just, wasting tons of energy.
And while Hess's law lets us calculate these perfect energy yields on a whiteboard, the real-world variables of moving pistons and heat loss will always take their cut.
They always take a cut. Which actually leads me to a lingering question I want to leave you, the listener, with today. Because, based on what we just learned about non-adiabatic combustion,
Right.
if heat transfer and piston movement constantly drain the energy potential of our fuel, what does that mean for the ultimate physical limits of our most advanced internal combustion engines?
It's a sobering thought.
It is. Like, how much of our fuel's ancient stored chemical energy are we forever doomed to lose just to warm up the cold metal of the engine block?
We can never be 100% efficient. The universe just doesn't allow it.
Exactly. Something to think about next time you start your car. Until next time, stay thermodynamically dangerous.